And I would like to talk for today and next time about what will be our final topic on the checklist. It is the traveling salesman problem, which is written on the list I wrote as TSP. That stands for the traveling salesman problem. The traveling salesman problem, which I write as, I will usually write TSP. All right. You will notice, I will say this again later on just to be clear, but there are two, if you're looking at the checklist, there are two topics at the end which we are not going to get to because we ran out of time. So the traveling salesman topics are the last ones that will appear on the tests and such. Anyway, let's talk about what the traveling salesman problem is. It's a particular problem, sort of a mathematical problem that is super important in the real world, and it has to do with Hamilton circuits in graph theory. So this is about the traveling salesman problem is about Hamilton circuits in a special type of graphs. It's about Hamilton circuits in what we call complete graphs. So I just want to say for a moment what a complete graph is. It's a special type of graph. A complete graph is one which, it's called complete because it has every possible edge in the graph. So a complete graph is one where all pairs of vertices have an edge connecting them. Every edge that might be in the graph is actually in the graph. There are no missing edges. That's why it's called a complete graph. So for example, if I have 3 vertices, what is the complete graph using those 3 vertices? It would be the graph that you get by including all possible edges. So there's an edge there, there's an edge there, and there's an edge there. Those are all the different possible edges you could have between those 2 vertices. So that right there, this is called the complete graph on 3 vertices. Right? That's the complete graph on 3 vertices. And there's another complete graph that you can get with 4 vertices. That would look like, I put my 4 guys here, and then I want to connect these all up in all possible ways. So like the upper left one is connected to 3 others. Here, here, and here. The one in the upper right is connected to all 3 others. Now I already have an edge across the top, but I get those 2, and I also need that one. That's a complete graph on 4 vertices. I could do this all day, right? Let's just try one more picture of a complete graph. Looks like if I have 5 vertices, you connect every one of them to every other one. So the one on top connects to all the others. Also, the one on the left side connects to all the others. That would look like this kind of thing. Also here and here and here. Looks like that. It's a nice symmetrical thing. All right, each of them are called complete graphs. When I draw a complete graph, it has some intersections in the middle, but that doesn't count as a vertex. Like this one here, there are only 4 vertices. It's true there's an intersection in the middle, but I'm not considering that to be another vertex. All right, that's what a complete graph is. A complete graph on 6 vertices, you could draw it. It's just sort of bigger and nastier, but it looks more or less like these things. All right. What about, so I said the traveling salesman problem is about Hamilton circuits in complete graphs. Can we think about what does a Hamilton circuit in a complete graph look like? So in here, remember a Hamilton circuit I hope you remember just what that means. That means a circuit in the graph which visits every vertex. A Hamilton circuit must visit every vertex with no repeats. All right, so what would that look like in let's say, a complete graph with 4 vertices? What does a Hamilton circuit look like? Let's say I'm going to start in the upper left corner. There's actually many ways to do it. Last time we were talking about graphs, and I said, can you find a Hamilton circuit? And it was not easy, in my opinion. In a complete graph, it's always easy to find a Hamilton circuit. For example, I could just go around the outer edge. That would make a Hamilton circuit. It would visit every vertex like this, right? That is an example of a Hamilton circuit. But I could also, if you want to be fancier about it, I could use some of the diagonals. So here's another way you can do it. I could go like this, down there, over there, over there, over there, right? That's another example of a Hamilton circuit, yeah?
But don't we have to like go to every vertex?
Yes.
And in the first picture we didn't go in the middle.
Yeah, this is the complete graph with 4 vertices. The thing in the middle doesn't count as a vertex.
Okay.
Yeah. Yeah, in all of these pictures, like this one has a lot of them. There will be crossings of the lines, but that doesn't count as a real vertex in the graph. Yeah, this can be slightly confusing. All right. A Hamilton circuit must visit every vertex with no repeats. If I were to, rather than drawing the pictures of the red lines like that, another way you could indicate the Hamilton circuits, if I gave them names here, if I just call these vertices A, B, C, D. This one that I drew there, starting at A, this one was A, C, B, D, A, right? This is another way you could indicate where the path is going. Actually, my picture is slightly ambiguous because I didn't put a little arrow about which direction around you're going. But certainly, if I write the letters, it's not ambiguous anymore. This circuit was A, C, B, D, A. You could also do A, B, C, D, A. That was actually around the edge. That was the first one that I drew here. Or I could do A, C, D, B, A. Did I say that already? No, I didn't. That's slightly different from what I said before. This would go down the diagonal, then across the bottom, then up the other diagonal, then across the top. All right? In fact, I would invite you to realize, actually, any sort of written out listing of the letters would count as a Hamilton circuit over here. Any rearrangement, I can start, let's just say I'm going to start at A. I can start and end at A, but any ordering of the letters will make a Hamilton circuit, right? And in this particular example, actually, there's 6 of them. I could go A, B, C, D, A. That's one. That's just kind of like ordinary alphabetical order. But I could also go A, B, D, C, A. I could also do A, C, B, D, A. I'm going to try and write them all down. I could do A, C, D, B, A. I could do A, D, B, C, A, or A, D, C, B, A. I think that's all of them. There are 6 possibilities in this particular example. Starting and ending at A. You can write the other ones in any order you like, and those are always going to be a Hamilton circuit in the original graph because I use each vertex one time. Now, ordinarily, you might have to worry about, like, for instance, here I put DB. Is there really an edge from D to B? The answer is yes. If you're talking about complete graphs, which we are from now on, then automatically every edge that you want to be in there is in there. And so these all make legal Hamilton circuits, all right? Okay, now I said that this was a super useful problem in the real world. This has all been fairly abstract. I want to try to talk about why this would come up in the real world. And here I have a real world scenario. The realness This is actually based on my real life. When, as you may know, when a mommy and a daddy love each other very much, they have kids, and at around the holiday time, I didn't really have to say that first part. Around the holiday time, my family with the kids, we have to visit each of the sets of grandparents, and there are some negotiations that have to happen about whose house are we actually going to be on Christmas at their house, or are we going to do it here this time? Anyway, we have to always sort of work out the details of this. And here's the scenario that we find ourselves in. Let's say this is like my actual house in Fairfield, Connecticut. Lovely Fairfield, Connecticut. Over here we have Nana and Grampy. Those are my parents who live in Massachusetts. We also have my wife's parents. They are known as Gigi and Pops. They live in New Jersey. We live more or less exactly in between, which is great. I mean, that was one of the reasons why I wanted to work at Fairfield University, our dear institution. And then we also want to go to Aunt Megan's. This is my wife's sister, Aunt Megan, who lives in Pennsylvania. All right. Sometimes Gigi and Pops will go to Aunt Megan's because Aunt Megan's house is bigger than Gigi and Pops's. So when everybody wants to come over, it's nicer to do it at Megan's house. This is all a true story. I am living that life. All right. Now, in some situations, on some holidays, actually, we want to go to all of these places within the span of a few days. Because like on Christmas or something, we want to hit everybody, right? And the question is, what's the best route to visit them all? And let's say I want to start and end at my home, the Star. This is home. All right. What's the best route? There are several ways that I can do this. And by best route, I don't really mean like which roads specifically should I drive in. I just mean like, should I go to Nana's first and then Megan's and then Gigi and Pops, or should I go some other ordering? All right. And what it comes down to is I have to think about this. There's sort of a graph here about all the different places that I could go to and the places I could drive from one to the next, right? And the question is, in this graph, I start here, and I want to visit each of the other three vertices once. Obviously, I don't want to repeat any of the vertices. What I'm talking about is running through this graph in some way to visit all four vertices and come back to where I started. That's a Hamilton circuit, right? I want to visit each of the vertices and end up back where I started. The best route to visit them all, starting and ending at my home. All right? I don't care about using all of the edges in this graph. That's not important, and I wouldn't want to drive all the edges. I just care about visiting each of the vertices. All right? So this is how Hamilton circuits occur in the real world. This is, can I just say, this will make a Hamilton circuit. And I'd like, when I'm, for the purposes of this problem, I want to minimize my total travel distance. I don't want to be like driving back and forth unnecessarily, all right? So this will make a Hamilton circuit in my graph, and I want to pick a Hamilton circuit which has a minimum total travel distance, all right? That's the most natural thing to do. Now, I will be honest, in my real life, I don't try to analyze this problem mathematically. We just kind of, well, to be honest, my wife usually figures out and decides where we're going to go, and I go along with it, and it's fine. Nobody cares that much in my real life. But There are some situations in real life when this problem is super important and people really care a lot about. So this is similar to, how about the guy or young lady driving the Amazon delivery truck. So this is similar to a delivery truck with, let's say, I don't know how many packages a typical truck like that has to deliver. Let's say they get, I don't know, 100 packages. To deliver to 100 different addresses. All right. This is like the blue Amazon truck has to deliver 100 packages to 100 different addresses. And now you have a pretty serious problem about how should I decide in what order am I going to deliver all the packages. All right. There's many of them. And there are very, very many different possible routes, possible orderings that I could possibly use here. I will say, in what order should we deliver them? All right. As far as I understand it, they do not leave it up to the driver of the truck to decide on their own what order we're going to deliver the packages in. I believe this is all sort of figured out ahead of time by the evil overlords at the Amazon Corporation. They just tell the driver, you go here and then here and then here. And they probably are like GPS tracking the driver at all times to make sure that they don't have any breaks or whatever. But this is a major mathematical problem that is very important to people like the Amazon Corporation. They want to be able to do this as efficiently as possible. If you end up driving extra distance, then you have to pay for more gas and pay for more time for your employees. So in what order should we deliver them? This is the problem, which we call the traveling salesman problem. Another way that this has sometimes been described in the past was like if you have a traveling salesman who's like selling typewriters to people, and that guy has to like go to a bunch of different houses and try to convince people to buy his typewriters. And that guy has the same kind of thing that he has to figure out. What's the route that I should use to visit all of these people in the most efficient way? All right. In what order should we deliver them? Which route to go? All right. All of this is about Hamilton circuits in complete graphs. This is called the traveling salesman problem. Although we don't really have traveling sales people anymore. But this is super important for package deliverers and so on. The traveling salesman problem. These kind of questions about efficient routing is also super important in like computer networks. You know, we have things called routers, and their job is to figure out the best path from your computer to whatever other computer you're trying to access information from. And they have to answer a similar thing. It's a different kind of question. It's not exactly the same, but it's similarly about finding best routes from one place to another. All right, anyway, let's see if we can try to work this problem very specifically. So what I've done is just back to this example of me and my family. I actually worked out, I went to the old Google Maps to determine the distances along each of these different routes. And I am going to tell you, so this is my driving problem. These are real numbers. I have 4 locations basically. One is sort of my home base in Connecticut. And then let's say I also have my parents in Massachusetts, Aunt Megan in Pennsylvania, and Gigi and Pops in New Jersey. All right. I'm drawing this. I'm not trying to draw this as geographically accurate. I'm just drawing it as an abstract graph because I don't care about making it look like the actual shape of the roads or anything like that. And I looked these distances up, and I have decided that if I drive straight from my house in Connecticut to my parents' house in Massachusetts, that's 156 miles. All right. What if I drive from Connecticut all the way to Megan's? That is 194, which I'll try to write on that edge right there. So each edge here represents one piece of this trip, and I'm telling you the distances for each one. The distance from Connecticut to New Jersey is 152. And I will just fill in the others. So we also have Pennsylvania to Massachusetts is 355. Pennsylvania to New Jersey is 114. And New Jersey, Massachusetts is 315. All right. Here we have all the information that we really need to find the best possible route. I have a distance for each of the individual sort of pieces of the trip. This right here, what I've drawn here, this is called a weighted graph. Right? It's a graph, obviously. Weighted means that in addition to being a graph, every edge has a weight on it. Those numbers there, we call them the weights. Now in this problem they represent distances, but in other problems they might represent, you know, money or some kind of a thing that you want to try to minimize typically. So this is a weighted graph, and what we want is we want the Hamilton circuit with minimum total weight. In this problem, the weights represent the distances. So I want the Hamilton circuit which has the minimum as small as possible to the total distance. All right? Now, how do we do that? There are actually a few different ways to do it, and we're going to talk about 3 ways to do this, as usual in this class. There's not just one way that you can solve a problem like this. We're going to talk about 3 different ways, and they are the 3 things, you see them on the checklist. The first one that I want to talk about, I'm going to talk about the first 2 today, and then the last one next time. The first one is the easiest from a theoretical point of view. I will say the simplest idea. In order to find the minimum total weight, we just write down all of the Hamilton circuits and then find which one is the minimum weight. Find which one has the smallest weight. All right? This is the simplest idea from an abstract point of view because it doesn't involve any kind of really fancy stuff. You just have to write them all down and check them all. It's not, this one might take you a few minutes to do, but it's not actually hard in terms of having any, smart, cute, tricky ideas. All right? This is referred to as the brute force method. Because you're not actually using any fancy ideas. All you're doing is checking all of the possibilities and making sure you choose the best one out of all the available ones. All right? So let's see if we can do this. Maybe I'll copy my picture down here just so I don't have to scroll over and over. I would like to write down all the Hamilton circuits, all of the hams. What I said before was any ordering of the 4 vertices will count as a Hamilton circuit. Now, I want to start at Connecticut and end at Connecticut each time, but I can write the other ones down in any order. So here's an example. How about, would you mind if these are the states. I'm just going to write the first letter just so that I don't confuse myself with the 2-letter abbreviations. So C means Connecticut. Here, maybe I'll just erase that other letter. All right. So this is the one which goes Connecticut and then up to Massachusetts and then down the diagonal to New Jersey, then up to Pennsylvania, then down the other diagonal back to Connecticut. All right. This is one possibility. Now, I'm going to write down all of the different possibilities. There should be 6 of them in this case. Really what it comes down to is I leave the C's like they are here, but I'm going to write down all possible reorderings of the 3 letters in the middle. And that there will be 6 alternatives. So there's one which starts with M there. There's one other way to start it with M, and it's like that, right? This is the way that I like to think about them, just to make sure I got them all. Putting M in this position, there are 2 different alternatives. Now there's also 2 ways I could do it with an N here, and also 2 ways I could do it with a P there. So next I'm going to put an N here, and then I could go MP, or I could go PM, right? And then finally I could put a P in the second position, and then go MN, or I could go CPNM. Ooh, look at that M. Has that extra little something for the weekend. Like that. All right, these are all the Hamilton circuits that are possible in this case. And we simply need to check the weight of each one of them. I say simply because it is simple. It's kind of a pain to do this. I'm going to make sure I have enough room here. Back it up. All right. We need to find the total weight of each. This involves adding together 4 numbers, really. So this one, CM and PC, I have to add together each of these little legs here. First, I go C to M. That's 156. So it's a 156 plus M to N. On the picture, that's the diagonal going down to the left. That's 315. Plus N to P, that's up the left side, 114. Plus P to C, that's 194. All right. Make sure you get all 4 of these numbers. Sometimes people forget to write the last one in there. Anyway, this is those 4 numbers. And then we add these together. I did this ahead of time on my calculator. I got 779. All right, so that's one of these possible trips. And then we do this 5 more times. That's why this is called the brute force method. There's not a lot to it, but you just have to do it over and over again. A computer is very good at doing this. A human being will get annoyed fairly quickly. That's all right. So anyway, again, we begin with C to M, which is 156. Next, I have M to P, which is across the top, 355. These will be different numbers, right? Next, P to N is down the left side, 114. Next, N to C is 152. These, when I added on my calculator, I got 777. It's a close call there, but I guess that's a little bit better than the first one. Remember, I'm looking for the minimum possible. And then the next one, CNMPC. That looks like C to N is 152. N to M, that's up the diagonal, that's 315. M to P is 355. P to C is 194. And this, when I add it up, I got 1016. All right? Would you mind if I just tell you the answers for the other 2? I hope that everybody gets the idea here. It's fairly tedious to work this through, especially with big numbers like this. On our test, by the way, I will not give you numbers that look like that. I will give you numbers like, 3 and 5 or something like that. Anyway, I will just tell you this one, when I added this up, I got 777. This one I got 1016, and this one I got 779. All right, those are the answers to the other parts. Anybody notice something interesting here about the numbers? What do you notice? And is there any reason for what you notice? Yeah?
They repeat, like for example, there are repetitions.
Yeah, right. These 3, the last 3 are actually the same 3 numbers. Why is that? This is not a coincidence, actually.
It's
Yeah.
going out of order. Like if you look at the order, for example, in the 79, in the first one you have Massachusetts, New Jersey, then Pennsylvania, and then it's just Pennsylvania, New Jersey, Massachusetts. So just switching the order.
Yeah. This is just the reversal of the first one. Like this last one here, CPNMC, that's the reverse of that one. All right. it's the same route really through the map. It's just that I went, one direction around the circle versus the other direction around the circle. Those are going to give me the same answer both times. So actually, when you're doing this brute force thing, it looks like you're going to have to check 6 of them. Really, you only need to check 3 of them. And when you're doing this on the homework or on a test or something, I would not expect you to actually add up all 6 of them. You should realize, you can write down all 6 of them, but then you will realize that some of them are duplicates of the other ones, just going in the opposite order. So those ones are reversals. Also, these 2 are reversals of one another, and these 2, whoa, something happened. I don't know what. Those 2 are reversals of one another. All right, so I will just say, like in the blue here, some are reversals. Sorry, something, okay. So we don't need to check them. Or I'll just say we don't need to add it up twice. All right, so you can write your big list of all the possibilities, but really you only have to add up for half of them because the other half will be reversals of the first half. All right. Great. Anyway, what's my conclusion, my final answer in this problem? What's the best route? It's this one, 777. Now you could write it either this way or this way. Those are both the same thing, just going in opposite directions. But just to conclude this particular problem, so here, our best route is Connecticut to New Jersey to Pennsylvania to Massachusetts to Connecticut. And I will just say, or the reverse. Either one that you say will be fine. Our best route is that, and the total distance will be 777. All right. This is how we do the brute force method for solving the traveling salesman problem. It really works. Any thoughts about that? I got one for you all to try, if you don't mind. This one, this is more typical for what you can expect to see on the test or on our homework as far as the numbers. So I didn't invent a silly story for this one. I will just say, how about that? All right. Here we have just A, B, C, D. Your job is to find the best possible Hamilton circuit, which is to say the minimum weight Hamilton circuit. Ordinarily, I would just say something like solve the traveling salesman problem here. That's your job, all right? What that means is, by brute force. Remember I said we're going to talk about 2 other ways to do this also.
Where do we start?
How about, I should probably tell you, starting at A. If I'm going to make them A, B, C, Ds, I'll usually just say start at A. But all right, you should begin by writing down all the possible different Hamilton circuits. A, B, C, D, A is one. Make sure you get 6 of them, and then add up the numbers for at least 3 of them.
Numbers.
The numbers. See what you think. I'll give you a moment. got 8 for the first one then.
That sure did.
Tester, question, are we just gonna find the smallest number, or we have to read the problem and then figure out the whole? Because if instead of like the smallest distance, it was like most amount of time to get from spot to spot, we want the smallest number, so.
Pretty much always want the smallest.
Okay.
Yeah. You might have to read some words and translate it into like visual.
Yeah.
Good.
Everybody's looking good. Maybe we can. I'll write down what I got. See if you agree. Can we talk about this? I hope that you feel like this is not hard to do. It's a little tedious since you're just adding these little numbers up one after another. But it's not. There's not a lot of thought that goes into it. You just got to make sure you're doing it right. So I did A, B, C, D, A for 8, A, B, D, C, A for 14, A, C, B, D, A for 12. I hope that you got similar numbers to this. You might have written them in a different order than I did, which is fine. Now that's only 3. There's really 6 that I should consider. The next one that I would write would be A, C, D, B, A. But that one is the same as this one reversed, right? It's the same as the second one here. So these two being the same, this one is going to add up to 14. I also have A, D, B, C, A. That's the same as something. That's the same as this guy here, right? So that's going to be 12. And then my last one would be A, D, C, B, A, which is the same as the first one, which is a 8. All right? I hope that everybody got those same results. And so, what's the...
The 8 looks like it's going like this.
Yeah, that 8.
It's having some fun.
Dancing. So what's the best route? It's the 8, and you could either write, the first one or the last one. Those are both the same. So the best route is A, B, C, D, A, or if you prefer A, D, C, B, A. You can write one or the other or both, whatever. For 8, all right. I might ask you what's the best route, and tell me how much the total weight is. Whatever. All right. This is the brute force procedure. Now, for the complete graph on 4 vertices, you have to check 6 different possibilities, which is a bit of a pain to do by hand, although if you're using a computer, it's no problem really. What about if you are checking more than 4 vertices here? If I went up to 5 vertices, actually there would be many more if I was doing A, B, C, D, E, and then back to A. There's a lot more rearrangements in that situation. This actually, if we have many vertices in the graph, there are, I will say, many routes to check. In fact, the number is something like, if you have n vertices, it's something like n factorial, which is very, very big. This is the same, we talked about this when we talked about different orderings, different permutations, like doing the Shapley-Shubik. This was important. I don't know if you remember that, but it also has to do with writing down all possible ways of reordering the other letters. And if there are a lot of letters, there are many, many routes to check. I will just say, even checking 10 different, with 10 vertices is, practically speaking, impossible to do. Certainly by hand, this would be impossible. Even if you're using a computer, this would be a very taxing computation. So even checking with 10 vertices is not practical. Not practical. Certainly by hand, you would never want to do any more than 4, really. But even using a computer with a fairly small number of vertices like this is not going to be practical. But think about the real world situation that I described. The Amazon guy wants to do this every day with 100 packages, right? That's basically way too hard to do this way, all right? The package delivery guy needs to solve this kind of a problem every day with, let's say, about 100 locations, right? This is simply impossible to do with, even if you're using a computer. What's interesting is, like, people have been working on this problem for a very long time because it's important in the real world, but there is no known solution that can efficiently compute the best route in a situation like this with, say, 100 different locations. Actually, no known algorithm, this meaning a computer program, or just sort of a strategy, a mathematical strategy, no known algorithm can find the best route in a reasonable amount of time. By reasonable, I mean, like, the package guy has to do this every day. And so if you are going to run a computer that takes 2 weeks to find the answer, that's not good enough because you got to do it every day. Yeah, question.
I'm pretty sure how they do it right now is they cluster the houses, so they'll take 100 houses and cluster into 8 segments. And
Yeah, right.
Hit each neighborhood, and then that's how they'll do it.
Yeah, I think in real life, for the package delivery guy, they have a bit of an advantage because they are basically going to places that are all along roads or something like that, and so you don't actually consider all possible orderings because most of them are ridiculous. You basically go along the road. So in practice, they have some kind of tricks that they can use based on the structure of the roads that helps them out. But as an abstract problem, there is no algorithm that can solve this. If you don't have, say, the houses clustered together in neighborhoods or something like that, there really is no known way to do this efficiently. This would come up, this sort of unrestricted version might come up if you were doing drone deliveries to random spots where you're not following roads and they're just spots everywhere that are not grouped together in some way. This kind of question is super important. That's all I'm saying. And there is no known algorithm that can find the best route in a reasonable amount of time. If you have to solve this same problem every day, but your supercomputer takes 3 days to solve the problem, then this is not good enough. So all of this to say, this brute force algorithm, what I want to impress on you, the brute force works, but at large scales, it is practically speaking unusable. At large scales, it's not practical to use brute force. Instead, there are various other sort of tricky methods for doing this. Now, I already said that no known algorithm can find the best route. So I will say instead, we use tricks to find what I would call pretty good routes, even if they are not the best. All right. So this is a true fact. In the real world, the Amazon trucks that are driving around, they are not driving the mathematically best route because it's actually impossible for them to compute mathematically what the best route is. They don't actually know that they are driving the best possible route. Instead, they use some tricks to figure out what a really good route is, and they do that instead, even though they don't know for sure that that's the best way to do it, because this is the state of the art in terms of mathematical technology. If you can figure out a method to find the best route in a traveling salesman problem, then tell me about it, and I will make a lot of money on your idea. This is something. If you actually are able to solve the traveling salesman problem, you could sell your idea to many corporations who would be very, very interested in it. It is not known how to do this, and there are many researchers who are actively working on this. Like, this problem has been around for over 100 years, and so people have been working on it for a long time, for entire careers spent on trying to solve the traveling salesman problem. All right. Anyway, we use tricks to find pretty good routes, even if they're not the best. These are referred to as approximate algorithms. Algorithm just means like a strategy for computing something. The approximate meaning not necessarily the best, but good enough. That's what I mean by approximate. All right. So there basically is only one way that you're guaranteed to do the best route, and that is the brute force, which is basically not practical to use in the real life. And so in real life, instead, they use what they call approximate algorithms. They are not necessarily going to give you the best answer, but they give you an answer that's pretty good, usually, hopefully. All right? And we are going to talk about two of them, one today, one next time. So let's just talk about the first one, the first approximate algorithm for the traveling salesman problem. It's actually very easy to do. It's called the nearest neighbor. It even has a cute name, the nearest neighbor algorithm. All right. So like on our test or homework or something, some problems I will say, solve this traveling salesman problem using brute force. Or I might say, solve this using the nearest neighbor. Or I might say the other one. It's called the sorted edges procedure, whatever. The nearest neighbor algorithm, okay? It's very easy to do. It's you have to think a little bit more than the brute force, in which you don't really have to think at all. But it's not hard, and it's much, much faster than the brute force. That's the whole point of this. It's much faster than brute force, I will say, although may not always give the best answer. That's the trade-off. All right. Anyway, let's just demonstrate with an example here. Let's do this with 4 vertices. But actually, if you're doing the nearest neighbor, you could fairly easily do this even with 10 vertices or far more, even by hand. I could do this on 50 vertices if you gave me a few minutes to do it. It's not hard to do. I'm not trying to flex. Any one of us could. Let's say my graph is like this with the ABCDs, and I will put some weights on them. Like so. All right. Is this the same graph as before? It's not. Anyway, here's the strategy. Here's how you do the nearest neighbor. So let's find a solution starting at A, just because I said so. with the nearest neighbor. I'm going to write NN for nearest neighbor. Here's the idea. You sort of, from the starting point, you choose edges as you go. And each time, use the cheapest available edge. I will say the cheapest legal edge. All right, so if I start at A, my first edge that I choose, I have three choices, right? I could use the 1, the 4, or the 5. I'm going to pick the 1. That's what I mean by the cheapest legal edge, all right? This is called the nearest neighbor because in each step, I'm choosing the nearest one, which would be the 1 rather than the 4 or the 5, which are further. If you interpret the numbers as distances, like we usually do, you choose the nearest one each time. I should just say, what exactly do I mean by legal edge? By legal edge, I mean you can only choose an edge to a vertex that you haven't visited yet, right? Because that's the whole point of the traveling salesman is you're not supposed to revisit vertices. So legal here means don't revisit any vertices. I will just say until the end. Of course, at the end you have to arrive back where you started, but don't come back to where you started before you're actually done with everything else. All right? Don't revisit any vertices until the very end. Okay, so let's try and do it in this example here. I find when I'm doing these, here's my, of course you can write this how you like, but here's my sort of tip about how I like to write this. Just sort of over to the side or something, make another grid just with points on it, and over here is where I'm gonna write my answer. I find if you start scribbling on top of this picture, you end up making a mess. Over here, I'm going to write my answer. Like I said, I begin at A. This is where we start. And first, I pick this edge for 1. That was my cheapest option available at that point. I went over here. All right, now, from B, I have 2 choices. Well, I have 3 choices, but I can't go back across this edge because I don't want to go back to A. So I can either go the diagonal down to C or straight down to D. Which one should I do? Go to C. Yeah, the diagonal is 1 rather than 2 here. So the next choice is here for 2. All right. Now from C, where can I go? On the graph here, so I just did that one, so I can't do that one. I got a 5 and a 3, but actually the 5 is not allowed at this point because I don't want to finish before I'm actually done with the whole thing, right? We need to visit every vertex. So I must go across to D here, which is nice. I mean, I didn't want to use that 5 edge anyway. So that's a 3. And now I've only got one choice. I got to go back to where we started, right? So I go D back to A for 4. All right, so my answer is A, B, C, D, A. And that's it. This is how you do the nearest neighbor algorithm. It's like, do you agree with me that it's very simple, and it really doesn't matter even if you had many vertices here. All you're doing is just choosing one route, and that's it. So this is my final answer. If you like, you could say this, the weight of that, you could add these numbers up. 1, 2, 3, and 4 makes 10, right? 1 plus 2 plus 3 plus 4. That's 10. I know that from bowling. That's how the bowling pins are arranged. All right. Any? Yes?
B to C is 1, right? Not 2.
Oh, okay. Forget I said anything about bowling. Yeah, sorry about that. The diagonal is a 2. Oh, no, I wrote it as a 2. It should be 1. Thank you for that. Now I feel foolish. 1 there. Okay, so it's not 10, it's 9. 1 plus 1 plus 3 plus 4 is 9. All right? That's really all there is to the nearest neighbor procedure. I hope you agree this is much easier to do than the brute force. The brute force, you have to check 6 different cases. This one, all you got to do is build one path as you go. All right? As I said before, the downside of this, this is much faster than brute force. But it doesn't always choose the best route. That's the problem. Doesn't always pick the best. I have just an example to demonstrate that fact. Check it out. What if I have this one here, and I go, how about this? 1, 1, 1, 2's on the diagonals, and then 1,000 over here. And let's say I go like this, A, B, C, D. And let's see what happens if we do the nearest neighbor in this case, starting at A. The nearest neighbor starting at A. This is an example where the nearest neighbor is going to make some bad decisions. Although you can't blame them, but unfortunately. If I do the nearest neighbor starting at A, where should I go first? You look at the 3 options, are the 1, the 2, the 1,000. Which one should I do first? Yeah? Yeah, you should go to B first. You take the cheapest edge every time, right? So it should go A across the top to B. That's the one. Now, from B, my choices are down the diagonal for 2 or down the side for 1. I pick the cheapest edge every time, which is down the side for 1. So this is a 1. Now, from the C, I could go up the diagonal. Actually, that's not allowed because then I would go home before I'm done with everything. I should go across the bottom for another 1. And now I am locked into taking the edge up the left side for 1,000. All right. This was a bad choice. Any reasonable person looking at this as on the whole will just say, okay, I definitely should not do the 1,000, in which case I should go sort of this kind of hourglass pattern would be better overall. That's taking a bird's eye view of the situation, but the nearest neighbor doesn't do that. The nearest neighbor just tries to make each choice the easiest choice in every individual step. And there's a life lesson here, isn't there? It's not always good to just do the easiest thing from one moment to the next. Sometimes you got to step back a little and take on some hardships in order to avoid hardships in the future. This is an example of somebody who's taking the easy way out every time, and then they get stuck into this bad situation over here. Anyway, this is an example where here the nearest neighbor chooses a bad answer. Right, 1,003 is the total weight. Actually, this is not the worst possible answer. The worst possible answer would go across the middle like this. The 2, 1, 2, and 1,000. That's 1,005, which is worse. But anyway, the nearest neighbor chooses a bad answer. That's gonna happen sometimes. Yeah.
Not like quite related to this, but say like if you are at like the starting point for A and A to D was 1 and A to B was 1, which one would you choose? Or does it matter?
Yes, sometimes there are ties. And if there's a tie, you should just choose one at random. And unfortunately, sometimes it does matter. On our tests, I'm going to make it so that you don't have to worry about ties, because I don't want to get into that. But yeah, if there are ties, you just have to choose one at random. All right, I got one more example for you all to try, and it's a larger graph, so I put it on a handout here. This actually has 2 sides, the same graph on both sides. If you remember, please bring this back next time, because we're going to, like I said, there's one more method we're going to talk about, and we will do that other method on the back. The 2 sides are the same. So your job is to find a good Hamilton circuit using the nearest neighbor starting at A. If you know what you're doing, this will only take, less than 1 minute, certainly. I have... This is what everybody got one, right? I hope you're looking at this. You can read that. Let's find the circuit using the nearest neighbor at A. The nearest neighbor algorithm starting at A. If you know what you're doing, you should find this very easy. I hope that you do.
Do you have to use all the lines?
No, you definitely will not use all the lines. You have to use all the letters. I'll give you a minute and then we'll talk about it. Can we talk about it? It's been about a minute. Unfortunately, you may realize that if you mess it up early in the problem, that you'll be screwed for the rest of the problem, unfortunately. Where do you go from A? You have 4 choices. I got a 7. This guy is a 1, a 3, or a 5. I pick the 1. So you should begin by going A to D. If for some reason you didn't see the 1 and you went to C instead, your answer is likely completely wrong. Unfortunately. Anyway, where do we go next? From D? So at this point, you should be looking at this, or that, and you just choose the best one. Which one is it? Up to B should go next, yeah. Now I'm at B. What do you say? Where did you go next from B? C. Down to C for 1, yeah. And then, maybe I'll write the numbers in here. This is a 1, a 2, a 1. Now from C, you could look over here. Actually, my only choices are, there's only 2 vertices sort of left to go here, but I don't want to go back to A because then I would finish prematurely, right? I have to actually go to C. That's my, to E. That's my only option at this point. That's a 4. And then back to A for 7. So these, if you want to add them up, or let me just say my final answer, it's A, D, B, C, E, A. And if you want to add them up, that would be 15.
But there's a better answer that gets you only 13.
Yes, so I was going to say, are you sure this is the best answer? And your answer should be, no, I'm not sure that this is the best answer. This is just the answer that you get when you use the nearest neighbor. It's not necessarily the best answer. And you think you can do it using 13?
Star.
If you make a star across the middle there?
Yeah.
Yeah, that would be a 1, 2, 3, 4, and 3. Yeah, that
yes.
sounds better
A, D, B,
than this to me. Yeah. So that if this was the question on the test, that is a wrong answer. I mean, that's because I said find the circuit using the nearest neighbor algorithm at the point A. This is different from find me the best possible Hamilton circuit in the graph. Yeah.
I was wondering what the appropriate manner to, like in the situation where, what if 2 of them were the same, like you were looking at?
Yeah, right. Then someone asked this before. If there's a tie somewhere, like in this case, actually from E, there are 2 edges with 4 on them, then you just would choose one at random. Although I'm going to try to make the example so that doesn't happen. So. Yes?
If, for example, we are already at E, and then we have to go back to A, but the way directly from E to A is 7, and if we would go from E to B and from B to A, and that would be less.
Mm-hmm.
Should we then say E to A or E to B to A?
I think the scenario you're describing would never happen. You say we get to E and we have to go back to E? To A?
Yeah, we just have to go back to A,
but that means that B has already been used, so you can't go back to B.
I know, but if the way would be shorter, then it would make more sense to go to E to B.
Oh, if this total was shorter?
Yeah.
Yeah. That's not a Hamilton circuit, though,
Okay.
if you repeat the B. So I agree. If you're trying to do this for some reason in real life, you should do what you said, but that's not That's not a Hamilton circuit, so that's not appropriate for answering these kinds of questions. Yeah. All right, this is the nearest neighbor algorithm. Now, I said we're going to have one more thing to talk about, and that is, it's called the sorted edges procedure. We have 10 more minutes today, which is not enough time to talk about that. So would you mind if we just stop now? And then next time we will talk about the sorted edges, and that'll do it. We do have homework. Oh, sorry, I meant to say we're going to have homework due next week. It'll be the last homework assignment, and because it's the last one, there are some problems about the sorted edges on the homework that's due on Wednesday. You will not learn about it until Tuesday. So those problems you'll have to wait until after next class. I hope that's